Good afternoon, ladies and gentlemen. Lovely to have you here. Thank you for coming, even though it's Sunday and lunchtime. I'm Nikki Curley. I'm a founder member of the Cowie Catchment Campaign here in Grahamstown, so care very much about water issues and also working at roads. So my role today is to make some introductions, and first and foremost, please check your cell phones, switch off the sound or switch them off completely, please. The other thing just to bear in mind, there's an exit. So if there's an emergency and you need to get out in a hurry, that's where you go. Don't panic, just proceed slowly. Okay, and then I'm going to introduce you to Kate. So, let me just find my page. Ladies and gentlemen, we are facing many pressing issues about water. Drought is impacting all of us. It's sharpening our awareness about the importance of water supplies, including an underappreciated resource, groundwater. It's a matter of time until everyone in the country will know what a hydrogeologist is. So, Kate Robey works for the Council for Geoscience, CGS, and she focuses on improving the utilisation of groundwater across South Africa. She recognized, even while she was studying here at Rhodes University, that groundwater is an underutilized resource that is becoming increasingly important in South Africa. Presently, up to 60% of South African towns depend solely or in part on groundwater. But there's a lack of knowledge and capacity in the sector, which often results in the groundwater supply schemes being poorly managed. Kate studied geology and completed her BSc and honours degree at Rhodes University. During her first year of employment at the CGS, working as a mapping geologist, she realized that she wanted her work to have a greater impact on communities. In all her work travels throughout the country, she saw what a difference water can make to a community and decided to change her focus to addressing groundwater issues. So, to that end, she completed her master's degree in hydrogeology at the University of Free State. She's keen to continue her research and provide solutions to communities in South Africa and equip every person on the street with the knowledge and skills to protect our precious water resources. Ladies and gentlemen, Kate Robey.
Thank you so much. Yeah. So, afternoon, ladies and gentlemen. Thank you so much for giving me the time to talk about something that's very important to me. So, as I said, the Council for Geoscience, I don't know how many of you know, but it is a parastatal. It's our geological survey of South Africa, and it's our mandate to do geoscience research. And as a hydrogeologist, my focus is on groundwater. It's also great to be a Rhodes alumni and be able to present to you on this stage about my research into the current and emerging issues surrounding groundwater in South Africa specifically. So, we all know life would not exist without water. And when we visualize it, we always think of these beautiful flowing rivers or crystal blue lakes. But this is really false advertising. I don't know how many of you know that. Sorry. Even though the earth is covered 2/3 with water, 97% of it is seawater. It's not readily available for us to consume or use. Only 3% of our world consists of fresh water. And of that, how many do you know that 1.3% of that is surface water? Your streams, your lakes, your dams, wetlands, 1.3%. 30% is actually groundwater, and that is the greatest distribution. So if you look there, that's at 1%. The rest of it is locked up in our ice caps and glaciers, and we're not readily available, and we don't want to be using it or taking it from that as we know the consequences of that. So worldwide, groundwater is actually the most readily available water resource available for fresh water. It's widely distributed. More than half of the population consumes groundwater on a daily basis. And this is not just the developing countries. This is majority of Europe depends on groundwater for their water supply. America, most of their crops actually use groundwater. So it's very important, and we've just got a terrible marketing agency. We need to change that around. Because really, I bet a few of you only recently know exactly what groundwater is and hydrogeology, and that it's important to us in the last 5 years. So exactly, what is groundwater? Well, it's the water that exists under our feet. It's found in the ground. You find it below this zone known as the water table. And below the water table, the ground is saturated completely with water. And that's what groundwater is regarded in the subsurface. It fills these little cracks and pore spaces in the subsurface. However, in South Africa, you can't just drill to the water table and have sufficient water supply. And worldwide, groundwater is regarded to be hosted in aquifers. So your rocks and your sediments that have enough pore space and interconnectivity that allows sufficient water to be supplied to you. So it all depends on the role. The aquifer that supports a spring might be very different to the aquifer that supports the borehole that you need to support a farm, to the aquifer that supports a well field that needs to supply Beaufort West. So it's all dependent on your aquifer, and we need geologists and hydrogeologists to understand this, to understand what is the interconnectivity, the pore space, and how we can utilize this water. So in South Africa, majority of our groundwater is found in a fractured rock. So a solid rock that is fractured. That's very important. And the maximum borehole depths, we know, really go to a depth of 150 meters. Generally, they can range up to 50 meters. It's all dependent once you hit the right resource with the right water quality. And also geology influences that, because groundwater flows a lot slower, years to tens of years. It all depends on how connected and what the rock type is. So it's very important to understand that. And because of our wide geological history, I don't know how many of you have been able to do some of these geological lectures or information, but we have a range of geological rocks, and they host and have different properties that affect our water supply. But it's not that complex. I also don't want to make this sound like you can't understand it. It's just you need to know the facts and how it influences it. Also, how many of you knew that 8% of South Africa actually contains 50% of our surface water? Also, 98% of our surface water is allocated for use. We can't actually develop our surface water any further. We need to protect it, because we've also been developing it for us, not for the ecosystems. So now there's a huge drive to protect our water systems, especially the surface water. We have so little. So the next readily available thing is groundwater, as I've said. It's such a huge component. You can look at other things like desalination, but those are costly and use a lot of energy, and they're always byproducts and stuff. Why don't we use groundwater? Also, our rain. I don't know how many of you know how little rain we actually get. Well, we get more. Our average is half the world's average. That's crazy. And then on top of that, 21% of this country receives less than 200 mils a year. And I know it's in the forefront because we are experiencing droughts, even on our water-rich areas like KwaZulu-Natal. And here's just a wonderful diagram showing how many towns utilize groundwater. That's up to 400. This is recent. This is 2004. Well, I used it, but this was worked out in 2013. So, like it was said in my introduction, about 60% of our towns use groundwater in your domestic water supply. And that can be ranging with combination with surface water and purely groundwater. That's a lot of people. And we actually have underutilized this resource. It's estimated that we can use double the amount and utilize it well if we develop. It's really the only last 20 years that groundwater has now become more important, especially with our previous government with apartheid. We marginalized a lot of the community, and we have been very effective in getting up to 95% of South Africans readily available to their water needs. And now we need to get that last 5%, which are often in remote areas like the Northern Cape, and there isn't surface water resources to develop, or have things like desalination to communities where they don't have the capacity or education to support such systems. Just to also give a little fun facts. I know the people in Grahamstown have relied on the spring for their drinking water, especially recently. I'm hearing the water quality is a problem here. So how many of you realize that groundwater actually, a spring is the surface water visualization of groundwater. It's where groundwater discharges at the surface. So that's your groundwater. Pretoria was developed because of its fantastic fountain springs. And that supported the city for 50 years. And it continues to support it. Our rooibos industry also in the Western Cape, totally unique to South Africa. We couldn't have it without this microclimate. We require groundwater for it, and there's need for research into what climate change might have on the effects of groundwater and how these farmers need to actually still continue producing the rooibos that we need. Even locally here, your citrus industry is supported by groundwater, and these are some of the towns that are totally dependent on groundwater and continue to be. So I hope I've just given you a good idea of how important groundwater is to South Africa. And now, and also the last 20 years, there's been such a drive to its exploration and quantification, so we actually know what we have. But that has also resulted in problems, and the current problems we're finding with using our groundwater. One of the forefront is acid mine drainage. As our mining industry is slowly declining, mines are getting abandoned or stopped. They're stopping pumping the water. They didn't actually, 100 years ago, consider the environmental impacts, the amount of the population growth. They were just going for a resource. And this is how also science is changing, especially in South Africa. We used to be totally about exploration and mining. Now we're looking at how tourism is important to us, how to fix these problems of the past. And this is where the future of especially the scientists, young scientists are going to go. And I really encourage you guys to think of innovative things on how we need to prevent these problems that are affecting all of us. Because without our water, we wouldn't have crops, we wouldn't survive. So that's one of our biggest issues. We also are now currently considered one of the approaches to alleviating drought situation. KZN, I've just put a lot of money into drilling a whole lot of boreholes to support the impacts of the drought. And then one of my main topics, which I have been focusing most since I left varsity, was giving capacity development and investigating in innovative ways to preventing problems with the management of the well fields, because that's often we make a well field. So well field is where you have a whole number of boreholes, so wells in a field, and you give it to the municipality or the town, and then you leave, and they don't have the capacity. Majority of them are surface water experts or background in that. They don't understand it, and they're often neglected, and this ultimately results in the misconception that the resource is not adequate, and that's the wrong thing. Also, we've got these emerging challenges, the future of South Africa, and I will talk about shale gas. There's also interesting stuff with CO2 capture and sequestration. We have to reduce our carbon footprint, especially we're still coal-driven with our energy source. So they're looking in ways how to reduce the CO2. And groundwater impacts on the aspect of how much we can take in or how is it going to affect our groundwater. So you have to look at also who's impacted as a result of us doing these things to mitigate climate change. And then also, I don't know if you can see that, but geothermal energy. There's a lot of research now going into it. We never really thought South Africa could be a geothermally energy-driven place. So geothermal energy is where you take water and you pump it down into the ground and it gets heated up and used for a process. There's actually now research that this actually could support some communities in Limpopo. So we need to know if we use surface water or if we use groundwater, what are the reactions? This affects the efficiency of the system. So it's every day we use groundwater. Am I hitting it to the wrong? There we go. Okay, so I'm going to now talk about what I've been focusing on. And I don't know how many of you have experienced it, and I'm going to say it's a similar thing of rust. Iron and manganese clogging of production boreholes. So there's iron oxidation, and it clogs up these boreholes significantly. And it's a worldwide problem, and it's a naturally occurring problem. It's not a health risk, but it's just one of these things that happens. And it has a huge problem in the sustainability of these well fields in supporting communities. As I said, it's not a health risk. No one likes drinking it. That's the problem. It's that rusty color, and it's got that metallic taste as if you've run too hard and you've got a bit of feels like you've got blood in your throat. So no one likes it. And then the main problem is that supply problem. It results in limiting the use of water, and then it increases costs, and we need to try and maintain the amount of money we spend on giving people good quality water. It's very important, because if you have to pay more money, it results in delays and problems. Okay. So this has also been going on for about 20 years with the development of well fields. South Africa has really focused on the monitoring and remediation treatments. So that's treating the problems. It's treating the clogging, it's treating these little microbiology bios that are resulting in the clogging, and it's very costly to maintain, and ultimately people actually ignore it, and they don't want to deal with it, and that means failure. Then that means water restrictions. That means unhappy consumers. It just delays the whole process, and it's so unnecessary. And the horrible fact is then it gives groundwater a bad name. So these are just some examples of how nasty it can look. And that's just being totally neglected when we really should be taking ownership of our resource. And it's not that costly to continuously monitor and fix the problem immediately, but we want to also prevent the problem. So this place, I don't know how many of you know in the Western Cape about the Atlantis Aquifer. It's a very important and innovative site in South Africa. It supports the town of Atlantis. It's on the west coast. It's very close to Coburg. And they actually have no surface water. They experience semi-arid conditions. They have no surface water, and you'd have to pump in water from quite a distance at quite a cost. So the clever guys at CSIR actually suggested, why don't we collect the storm water? So there's not that much, but also the treated domestic water. And they capture it and they artificially recharge it in wetlands, because this area is comprised of wonderful sand, this really nice clean quartz sand. There are not many places in South Africa that have it, but this happens all over the world. The Netherlands would not have water if they didn't do the same approach of capturing their water and putting it back in the ground for storage and not letting it get wasted and going into the sea. So it's really an interesting place, and this has been going on for 30 years. And I didn't know about that until I started looking into it. So Atlantis is supplied by well fields, the ones called the Witstrand, but sadly the last 10, 15 years, it's got iron clogging. It's a naturally occurring thing that just happens. And look how nasty the water has. And it ruins the boreholes. The town used to be 100% supplied by groundwater. Today, it's only 30% because of the clogging reactions. And it's actually, at the moment, offline because they are spending a lot of money on rehabilitation. And the rehabilitation they have to do now requires a lot of chemicals. So there's always an impact as a result of leaving something. So I had this wonderful opportunity to look into preventing the source of the problem, preventing the iron getting to the borehole. And this was not innovative to South Africa and new to South Africa, but it's been going on a long time. This is called in situ iron removal. It's making the reaction go back in the aquifer. And I know this is going to sound a little counterintuitive, but we're going to make the reaction which precipitates the iron on the borehole, we're going to put it back in the aquifer. So the reason the iron is available is because there's no oxygen in the water in the aquifer. And when you do pumping, air comes and it aerates, and there's the reactions and precipitates there in the aquifer. Now we're going to do it away from the borehole, back into the aquifer. And it does work. As you can see, it's been going on for a long time. It's applied all over, and I'll explain the little dynamics as to why it does work. Even some interesting facts, it's used in Bangladesh at the moment for arsenic removal. It's very important there, and it's quite easy. And even in Egypt, they've got manganese issues, and they're using it. So, as I said, you need to take this oxygen pool, groundwater out, and you aerate it. You either use air or you use oxygen gas. Okay? You make it very rich in oxygen, oxidizing, and you pump it back into the aquifer at quite a rate and quite a volume. And that precipitates the iron onto the aquifer grains. They only do it in primary, so these sand aquifers, but we are now starting research in fractures aquifers, but primarily done in these sand aquifers. So on these grains, you have precipitation. The reason it works in a way is because the reaction's happening on a bigger surface area, not just on the borehole screening. And once you create this oxidation zone, you then start pumping water out again. Oh, sorry. And as you pump this iron-rich water that's not oxidized, and there's no more free oxygen to oxidize it out, it goes and it reacts with that oxidation on those grains, and it actually adsorbs. So adsorption is it's a bit like Velcro. You throw a ball on. Imagine Velcro and you're throwing a ball that can stick on Velcro. You're sticking those mobile iron manganese ions onto the grain. And this is a cyclic thing where you do it continuously. It's a management program to prevent problems. So you're always injecting an oxygen-rich volume for a certain period of time. And you oxidize, adsorb, oxidize, adsorb. It's actually the same process as they do for iron removal on surface, but we're doing it in the ground. And it's a lot cheaper because you need to always regenerate those filters above surface with these chemicals. And there's no waste here. So this is why it's quite interesting. And we're finding even though there's no health risks, you want your iron concentration by World Health Organization to be about 0.3. It prevents the quality and clogging issues at those concentrations above it. And in this example in the Netherlands, they would treat it, so it was below, and as you carried on pumping a volume, the iron increased. But by cycle 9, you were getting levels significantly lower than what it is. And this is a long-term plan. It happens in the ground, and it's a removal process that will continuously work. And this is one of the ideal things. It reduces above groundwater treatment. And it's actually why it was developed. It wasn't developed for preventing clogging of production boreholes. It was about actually making cleaner water. So it's used for that, and it's used worldwide. And we don't have byproduct or by-waste, and we don't have to play with nasty chemicals like chlorine gas, certain stuff like that, because that all adds cost. And especially in South Africa and Africa, we need to reduce costs. We need people to be able to understand. We don't want to be, I don't know how many of you guys have to do procurement, but it's awful getting 3 quotes for something. So it's about trying to make it as simple as possible and readily available to everyone. And one of the interesting facts, they couldn't understand why this process worked and wasn't clogging the aquifer or the borehole. And so now after 40 years and 30 years, there have been 3 studies where they've looked at these long-term sites. And they found that the boreholes are not clogging, so there's no need for this expensive rehabilitation, and that the grains were very small, and they weren't resulting in the reduction in the water's capacity to movement. So this is why this treatment is very interesting, and it also stops promoting iron release in those conditions. So it's been proven as to why, and these are the reactions and how it differs from the production borehole. So one of the great benefits of this treatment. So I got to do it in Atlantis because we needed to do something with Atlantis, and we need to continue supplying that community because especially in the Western Cape, we're also struggling from water supply issues, and they're taking some of our surface water to supplement their demand because they don't have. So we had our site, and we also, with science, you always have to have an idea what you want to, you have to work out how successful your treatment was. So we wanted the range of 0.3. On average, our iron was only 0.5, but it was causing such problems, and it ranged. It ranged up to 15 milligrams per liter but the average was a 0.5. So it was going to be quite interesting to see if we got that drop of 0.2. We had to inject it also up gradient of the water flow. So you would pump in that oxidizing water to this production borehole, and hopefully that oxidizing zone would be created. But then we had to be innovative. I couldn't use air because we have something called dissolved organic carbon, and that eats up the air, dissolved oxygen that's created by air before you even target your iron. So the next option to use is oxygen gas, and I was not going to play with oxygen gas. I didn't want to do the environmental impact assessment. And I don't know how many of you guys have seen Dr. Graham's experiment where he literally blows up the oxygen gas. And Atlantis is also a very low-income drug haven. I was not going to go that route. So I was looking at oxidants, and I came across ozone. And ozone's unstable at surface. We know we all need it for us to be protected from the sun, but you can actually create it, and you can buy it off the shelf. Someone can make it for you quite easily. It's very oxidizing as a gas form, but when you dissolve it in water, it's 18 times more soluble in water, and it creates a dissolved oxygen concentration, which is what I want. So we went that route, and it never had been applied before. So it's also the fun things, and you just need to plug it into the electricity, and it sucks in air, makes oxygen gas, and then it excites the oxygen gas, so they split from being O2 to O3. Very unstable, so you pump it straight into the water, and then it makes this dissolved oxygen that we want. Sorry. So this was the design, very rudimental, and that's what we wanted. We wanted something that would be simple, that I could make. I couldn't carry big things around. I had to set it all up. And we wanted to see how successful something like this is. We're going to use some engineers now and make something fancy. But we really actually wanted to see what we could buy from local stores. Yes, we had to get the ozone machine from a specialist, but we wanted to do that approach because that's what we want to do. We want to be able to go to farmers and assist them. It shouldn't be some expensive treatment that is not tangible or realistic to other people. So that was one of the goals of my research. So we would abstract straight from the borehole. We would aerate it, try and get as much dissolved carbon out. Also, we had hydrogen sulfide. We want to get rid of that. And then we would ozonate it, and we pumped it into this borehole. Very rudimental. And I'm showing the slide especially, because especially the young scientists, you are going to fail, and there's nothing wrong with failure, because you need to learn. You're going to try an approach, and it might not work, and you need to then evaluate why. And this was what happened when we first tried. It was a disaster. It wouldn't pump in. We weren't getting any dissolved oxygen in the production borehole, and it was quite frustrating. We actually had to hold the pipe down to try because it would just fling out. So then we realized there was gas bubbles, and that was affecting us getting the water into the aquifer to do the reactions. So it's very important to just also play and experiment. So at last we got it in, and we were seeing reactions, and we saw some great results where the dissolved oxygen was within what oxygen gas would expect it to get, and much higher than aeration, which was wonderful to see. However, our results were awful. They were making no trend. They were very erratic, and I couldn't understand how high they were compared to the baseline. So we decided maybe the volume was too small, and we had to inject a third time, and we went closer. So I was doing it at 10 meters from my production borehole, and I went 4 meters. And we slowly started seeing something again. But also, manganese didn't want to play at all. But the iron, that showed the trend, but also very high. Our dissolved ozone was great. It was showing exactly what we expected from the last test. So we were learning stuff. And it was great to see how easy it was and what the dissolved oxygen concentrations we were getting. And then we got to number 4. So with the first 3, I was doing a stop-start reaction. I was pumping out water and then injecting it. That was resulting in these erratic things, and with the iron clogging, not clogging, but there was just, the water was resulting in these iron concentrations that we didn't expect. So we had to try another approach where you pump and inject at the same time. And at last, I saw the results I wanted. So it was really great to see these reactions. We didn't have similar dissolved oxygens, but we saw what we wanted. Manganese doesn't do that same trend, but we're going to do longer tests to see. But it was great to see that we had these results. The best results actually were, this is the normal dissolved oxygen concentration in the aquifer. It's about 0.4 milligrams per liter. It's nothing. And with our treatments, our dissolved oxygen stayed. This period is where there's no injection. It slowly increased and it was residual. And we didn't expect that in a very oxygen-poor environment. And it's really great to see. And we're going to now do further tests to see if we can get these results or see different reactions. And so that's my future research. So iron clogging is a reality that a lot of production boreholes and well fields struggle with, and we need to find solutions that treat the source of the problem, not the problems, because it's never going to go away. And there is some really new research. We're actually busy patenting this approach because it's never been done before, and we hope that it will be a promising technique also for fractured aquifers in South Africa, because, again, I'm only going to be assisting about 3% of the aquifers. So we want to see how useful it is as fractured aquifers. And now I'm going to get into the emerging issues and what's going to become a big thing in South Africa with shale gas in our groundwater. So there is a belief that we have shale gas in South Africa, in the Karoo, and that place is semi-arid. And I'm mainly going to focus on not the surface water contamination or the contamination as a result of drilling. My focus area at the moment is what is at depth. We barely know what the water quality is like below 300 meters to about 3 kilometers. So we need to understand that. And so this is where our focus area has become, especially at the Council for Geoscience. So I don't know how many of you know exactly what shale gas is. It is an organic, rich shale. It's made of silts and mudstones that have been compacted and with heat and temperature have gone actually through the oil window into a gas. And we're mainly targeting the methane in that shale. It's only become important to us because in the last 15 years, the states have developed a way of actually getting this. Because shales are awful. They have very little pore space, and they're very tight. There's not that interconnectivity. So they have to fracture it to release their gas, to let it go, and let it movement. So that's one of the reasons it's never been considered as a resource or fossil fuel. So and it's different to coal. Coal is made from plants. We're land plants based. We're looking at sediments that were deposited in anoxic, so oxygen-poor environments, deep lakes, very little disruption, and it's like plankton and buggies in there. So there's a big difference between our coal and shale gas. And I don't know how many people know the difference of that. Just want to check. Okay. So why is it important to South Africa? So once the shale plays got identified in America, worldwide, and that they knew they could utilize it as a resource. Worldwide, they looked at similar environments that would have formed the same potential of having shale gas. So in South Africa, we have the Karoo Basin, as most of you know, and there are shales in here that developed in about the 280 million years period. South Africa was moving away from the South Pole. We had gone from the glacial dichotillite, and now we were going into deep inland sea, freshwater, similar to what the Black Sea is today, if you wanted to think of equivalents. So we are targeting the Echo group formations, the shales. Now you want the shales there. So I know majority of you who've driven the N1 will recognize the site. We want to get this White Hill target on the N1 around Lanesburg. You will look out for it. Here it looks white, but that's because of just weathering and decompression with being exposed to the surface. But these, the shale, the Prince Albert and the White Hill formations are what they're looking for. So just to give you a little bit of a idea of what our targets. And do we have shale plays? Now, in the 1970s, another government organization, they've now don't exist, was called Sucor, and they looked for oil. So they did a number of boreholes, deep boreholes to up to about 3 kilometers, looking for oil potential in South Africa. Shale gas wasn't even known then, or that we could utilize it. And they didn't find any oil, but they did find gas, because it wasn't a realistic thing to exploit. We didn't look at it further. But this is what is based on us thinking we have a shale gas play. The cause then, that information. So we are lacking. That information was collected for oil. So we are basing a lot of the stuff, a lot of people are basing that information on us having a shale play on old cores. So it's something to, but there is gas. Again, this gas we don't actually know exactly what it's comprised of. Either we didn't have the techniques or we didn't need to know. So it does exist in some springs and some groundwater. But why are people up in arms again? Well, the Karoo is very dry. Its name comes from the Khoi word, dry. It has very little recharge. So our aquifers only get 1 to 3%, and that has only been realized in the last 3 years. That's exactly how much recharge our aquifers get. So this is a limited resource that needs to be protected. A lot of farmers rely, and towns, completely on groundwater. So we need to understand it. And we generally have, it is generally low yield, so it can less than 5 liters per second. But in some situations, if you hit a proper fractured aquifer and these sills or these ring structures that are fascinating, you could even get about 80 liters per second. So there is water. But that water also, it wasn't long term, it's short lived, but it does exist. Generally, the water quality is more salty, high electroconductivity, so a lot of salts in it, but it's drinkable. And a lot of people rely on it, and we need to protect it. But like I've said, there's little research. And I know people there's a lot of opposition against it, but we need to actually, as scientists, need to understand what our shale gas potential is. We need to know what the geology is with depth, because again, this concern about contamination of our shallow aquifer systems. What are the pathways? Are these fractures from the dolerites, sills, and dikes going to transmit these chemicals that are used in hydraulic fracturing and contaminate our shallow aquifers? So we need to understand, but we can't, because it's underground, we can't understand without drilling. It's a necessary evil. Well, I wouldn't say evil, but it has to be understood, and we are in that process. There are currently 2 projects, and there are other projects, but in terms of drilling, there are 2 projects currently, one with the Council for Geoscience, and the other with Samera. It's managed by University of Johannesburg, and we're drilling deep with the aim of looking at the stratigraphy, so the geology. There is looking at some of the gas, but it's for pure research. There's no hydraulic fracturing of it. It's just looking at what exists. And we're looking at the shallow groundwater and the deep groundwater. And the deep groundwater had never been sampled before because it's not, mining didn't need it. Research projects didn't need it. If you got water, you actually hated it because it affected your drilling projects and cost you more. So it's often been ignored. And now these research projects have taken it extreme. So the one was about 670 meters in the Tanque Karoo. We were looking at that. And we recently finished the one in Willowvale. That was about 2.3 kilometers. I'm going to talk a little bit about the water in the Tanque one. But ironically enough, we didn't hit any deep groundwater in the Willowvale. There was nothing. It was dry. We did case off the shallow aquifers, but other than that, it was absolutely dry. It all depends on the interconnectivity. There might be water hosted, but if you don't have connections, it's not going to exist. So, very interesting. And then now, the CGS we're doing, we're going to drill 3-kilometer borehole in Beaufort West, around that area. We are doing all the baseline studies on the environment and the water quality before, and then only going to look at the drilling and those aspects. So all this information is to add to everyone knowing what we have and to actually make better regulations, because we have started the regulations, but they're also based on America's experience, and we have a totally different environment to America, and they also went ahead without doing the baseline knowledge or understanding our environment. So that's the biggest aspect. A lot of this research is being done. I know also in the Eastern Cape, they're doing a lot on baseline water chemistry and understanding exactly what we have before anything happens. So just to emphasize, we don't know much below 300 meters of the water chemistry or quality or rates or temperatures. It's all based on these hot springs or what we experienced with the Sucor boreholes in the 1970s. And I know that, again, when people aren't interested in the water chemistry, I struggle to trust some of the information given. I have to acknowledge it and use it, but I don't know how realistic the equipment was, their calibrations. You have to realize who is taking these measurements. And so we're aware that there's saline groundwater in the Aquifer because of that experience recorded, but I don't know who sampled it and how well they preserved the sample or if there was any contamination. So we have to be very responsible in our water chemistry collection and knowledge. So we are also doing, every site we do a 10K radius at least of the groundwater quality in the shallow. And we understand that before we start drilling to really see if there is any changes and to account for it, because it is necessary. We're also now starting to do geophysical logging, and that's going to assist us understanding exactly also parameters and what aquifers we actually are intersecting with depth, and just get a better idea, which is new also. We've never done it for any boreholes in South Africa, and at last we are actually collecting this data to better understand what is going down there and why it's important. And I'm going to just talk a little bit about the Tanque Karoo borehole we drilled. So up to about 560 meters, we also hit no water. We actually lost water. And I had already done the water chemistry, and it was very brackish there. I hated drinking the water. But it was acceptable, and the farmers lived and they were farming there. And ironically enough, at 560 meters, we hit artesian water, so water that flows out. It has enough pressure to be brought to surface. And ironically enough, it was of such a fresh quality, I actually had to drink it myself because I couldn't believe my probes were giving me those readings. We never expected that. It's never been recorded. Also, it was about 35 to 40 degree heat. That wasn't expected at all. And it was coming from a shale. You expect shales to be more salty, and because of the residence time and the composition of the rock. So that indicated that somehow, and now we're in a very arid environment, there's fresh water easily transmitted. And it was interesting because we're always expecting very brackish, and that's going to contaminate. And then ironically enough, we hit fresh, better water than anyone else has. And I did a 15-kilometer radius. And it was amazing to find that. And we did plug that because that was a requirement with the drilling operation. So it is a pity, but at least we know it exists there, and we've got the water chemistry, and we're busy interpreting it at the moment. So in the future, we might be surprised, and maybe these deep aquifers that we might target might be better water supplies than the shallow ones. So it's also very interesting. We need to know this because this might support better development. So to summarize this research, we must remember that the estimations on whether we have a shale gas play are based on old data that wasn't even looking at shale gas. Very important to know that there are a lot of unknowns, and we need to actually know them before anything starts. There are research projects going, and we're trying to attempt them as best as we can, and we also need to develop capacity. We can't have people coming from the States or the UK saying this is the way it's done. We actually need experts who understand our environment and protect our environment, but understand what they're saying. So it's also important that we have this opportunity to do these drilling projects. And I am totally pro for public pressure and awareness and opposition, because it's made everyone better. It's made everyone a scientist in some ways, and it's making you take responsibility of your resource. It's making me also take responsibility on how I conduct my research, how I give it to you, present it to you. You can't have people who fly by the night and tell you rubbish, because you can actually say, actually, I know that. And in the end, by you taking public responsibility of your resource, we are now going to start managing our surface and our groundwater resources better. And as a result, we all now are aware of what we have and what we don't have and how we must protect it. So I think it's great. And in closing, I would just like to say again that we have the hydrological cycle is this wonderful continuous cycle, but there are limitations. You can't just have your tap open running. There's a lot of money going into giving you that water, and we need to prioritize and protect them so that everyone benefits. We have to work together so that we all have a sustainable economy, which is so important to us, that everyone has fresh water, that they are really accessible. And I would like to acknowledge following organizations, especially for supporting my research, allowing me to use these sites, especially the Water Research Commission. They do wonderful research, and they are so supportive of young scientists, and I would highly recommend you guys to look at their website and contact the people there, because they are great at supporting young scientists, and also the CGS and Samira. And yeah, thank you so much. And any questions?
Thank you very much. That was incredibly informative. I think everybody in the room here has learned something new. We've got 15 minutes, so I think questions would be welcomed. Let's go one at a time. And please, the younger people in the audience, don't be shy. Here's our first question.
Relatively simple question. It relates to your oxidization of the water coming from the... it relates to the oxidization of the water coming from your aquifer. You were pumping the water from the aquifer in your diagram into a holding tank where it was being oxidized, and then it pumped back down again to oxidize the iron in the water below. That's right. Okay, so why is the water that's coming up from the aquifer not then being oxidized and clogging on the way up? That's my first question.
So you actually need to pump it at a specific rate. That is one of the other issues. If they pumped it at the right sustainable rate where there wouldn't be enough turbulence, these reactions with the oxidation wouldn't be so severe, and it wouldn't have the result it is. Often, when you have a water restrictions or problems, they pump it too high. The irony is my research wouldn't be necessary if people actually did what was asked for. So also, so that's why actually overseas it's used more for improving water quality, so they don't need to do as much treatment above surface. And so that's exactly.
Okay, then a follow-on question from that. As the water's now going back and it's oxidized, and you're getting your little iron particles sticking onto the other grains, now you've got a different environment down below there, as far as I understand. And so won't that over a long period of time change the quality of the water in the aquifer?
I agree. Okay, yeah. So the concern, it all depends on the aquifer and what it is, but it's removing the iron and manganese, which is a contaminant, and it's not affecting things like alkalinity or the pH or something like that. Irony is the oxidation reaction at the subsurface, at the borehole could result, because it releases protons, so it can actually result in acid, reducing the pH in the water. That's found really in the Table Mountain Group aquifers. So this doesn't have such a effect. It's actually, they are finding generally it's improving the water quality. It's removing things like arsenic and phosphate. And because it's forming oxides, and because generally the iron and the manganese and stuff is coming from sulfides or carbonates, the oxides are much more resilient to any mobilization back into that environment. And also the microbiology, there's that argument that the microbes are going to go big and bloom, but they're saying that, and I have to base it on research that's been published, because I haven't investigated it, is that the reaction, the oxidation reaction, the chemical reaction takes a lot faster than the microbes can get there, because it's a much bigger surface area compared to the borehole. They can't actually compete. So it's quite interesting on how that, and that's, I've just got funding now to carry on doing that research.
Very interesting, thank you.
Thanks.
All right, we'll take the next question along. Thank you.
You've actually answered some of my questions, but what I was concerned about is that the amounts of carbon, organic, dissolved organic carbon, and you also had H2S, which indicate that that water is fairly contaminated. Are there nutrients there as well? Because if that would suck up your oxygen, quite a lot of it. We have a high oxygen demand if you have nutrients over there, and that might be, slow the thing down basically.
So the irony is the dissolved oxygen is coming from the artificial recharge. So they're not cleaning it out enough with the to prevent that organics, and they've also put sometimes some industrial domestic waste into the recharge, but they are now working at removing it. So naturally, it never had that concentration of DOC. But we're lucky we also have enough carbonates and stuff that will buffer any release of. So there's no problem about. Because that would be a concern with also looking at like stuff with sandstones. They might not have that buffer effect. So we also have to research in that aspect.
The other question I wanted to ask was the pH. You using oxygen to control it, but if you control the pH, it would also allow the iron to sediment out, to come out of dissolved state, basically.
But then you have to add some nasty chemicals. And it's all those things. And I do know ozone is also quite and also expensive. So, but I didn't want to play. It also came down to me not wanting to play with some of the chemicals or buying them. So,
Thanks.
Thank you.
Right, let's get some more questions. Here's a question at the front. Could we pass the mic down, please? Thank you.
Hi. You'll have to excuse my ignorance, but from Queenstown area, our problem is not, as far as I know, iron, but more the lime.
The lime. And it's clogging your...
Well, it's, all of us is trying to go for alternative energy sources, which we can't use because it's clogging up that systems. So is there something similar to this that can prevent that?
I would have to look into it, and I would be very happy to take your details and maybe look into some of the stuff that is currently done and associated with that result because of that. So, let's chat later. Sorry, I can't answer it right now.
That's great. It's always good to get new and interesting questions. We'll take the microphone up here. Thank you.
Hey there.
Hi.
Are you familiar with the GRACE satellites and how it can map groundwater or the water tables?
The water tables and the variation,
Okay.
I'm not personally, but I know some colleagues are looking at that and how abstraction's affecting it, and it's very interesting.
So there's two satellites that go around the Earth, and when one is going over something that's more dense, it kind of gets tugged. and then the next one kind of gets tugged too, and just from that little tug, they can measure the amount of density that's below the satellites. And so the first time it went around, it just kind of mapped the baseline of the Earth. And then the next time it went around, it was it's measuring all the water. Yeah. And that wasn't something that it was really made to do, but it's really helped us be able to notice how Greenland loses its ice, but it's really precise to where it can measure groundwater as well, which is pretty interesting.
That'll be great, yeah.
And there's going to be a follow-on mission to that GRACE follow-on that will be even more precise.
Okay.
So hopefully that can help you guys at least get a sense of, you know, a macro amount of water that's below.
Exactly, and how things are impacted by it. Because
so you don't have to go, is it here?
Yeah.
Is it here?
Exactly. Yeah. Great.
Right, up there at the
There's
back.
one just before.
Thank you.
Yep.
Sorry, ma'am. Do you think that groundwater could be a solution to our current national drought?
I do. It's going to supplement and it's going to help, but again, it can't just be a slapdash, just drill boreholes, and we need to manage it. This is the biggest problem, is people, it will be and it will help, but you have to understand the system and you need to manage it properly. And we really need the capacity. There's so few hydrogeologists actually, and we need more people, and it needs to be a common thing, like as much as surface water engineers are common. We need groundwater engineers, because someone like me is focusing on the water chemistry. That's very different to someone else who's focusing on the water supply, and we can't all be experts in one thing. You actually need to also specialize in certain ways to get more answers and stuff. But it is often next done, and but we need to actually manage it properly.
Right, there's a question here.
Hello. I've got two quick questions.
Yeah.
Firstly, as you mentioned, in KwaZulu-Natal they're doing a lot of borehole drilling currently.
Yeah.
One of the concerns that was raised there was the drying up of wetlands as a result of overexploitation of the groundwater resource. What are your comments there?
Well, they should already, before you drill, you have to have those buffer zones, and normally they would, when you go and look at the hydro sensors, so you do a study area and you would see what is dependent. And we're supposed to do that sustainability thing where you pump a certain amount, and it all depends on the consultant and stuff, because they should be aware of what is dependent on the groundwater. So wetlands are supported by groundwater, so it is something that needs to be acknowledged. And Department of Water Affairs and Sanitation is supposed to be also making sure that those areas are protected with Department of Environmental Affairs. And it is often taken into account when a hydrogeologist does look for sites and utilisation. Yeah.
Unfortunately, sometimes it's not foreseen when something like that happens.
Yeah, sadly it's true. The same could also be said about dams, building a dam and you silting up an environment. But it's all, we all need to just try and do the best we can and learn from our mistakes and try and improve them.
Okay, thank you. And secondly, the water that you found in the Tankwa Karoo, down at 500 or so meters below, is it known which rock formation carries that water? You said it was in shale.
It was in the shale, it was in the Eka group. I must just make sure, because there was actually duplication, so it's either in the Whitehill or the Prince Albert formation.
Roughly this similar formation that they want to fracture hydraulically.
Yeah, but...
And it's pristine water, you say?
Yeah, it's of a drink. I don't know what's in, like what are the little, what makes it up, so the sodium chloride at the moment. I'm still waiting for those results, but it's of a drinking water quality, the pH, it's a perfect standard of that. And I didn't get sick afterwards, so we can always review that aspect. So, it's very interesting. Oh.
Very relevant question, thank you. What about down here in the front? Any questions here? Don't be shy, there's no such thing as a stupid question. Yes?
I was going to ask, you know how you wanted to release the gas in the shale gas. I wondered what's going to happen to the indigenous and endemic plants in the areas in which you are going to be releasing the gas, because as you said that when you drill into the rocks, there's a lot of contamination that happens. So are you going to move the plants to another area, or what's going to happen to them?
So I'm not an expert on this, but I can answer as best as I can on the knowledge I have. So again, the Environmental Protection Agency of the US actually recently released a study where they found that contamination does not happen if you do the best practices. Again, it's all about not doing best practices. But again, we all try and do the best practice, and people do also take shortcuts. So in terms of that, with the methane, it's supposed to be a borehole that goes, a fracking hole needs to be cased about 3 times with cement. So they're supposed to try and keep whatever comes up in that borehole. So the major concern would be the impacts of if there's outflowing and surface contamination on the vegetation. But again, they're supposed to do baselines, understand if there is any important plants over there, then there might be restrictions. You can't actually go and do hydraulic fracturing there. So there's a whole lot of, and this is what our legislation and scientists are trying to do and realizing, because again, the crew is very sensitive, need to be aware of what we have and how to protect it. I hope that answers as best I can.
Good to see some budding botanists here. Yeah. Any other questions? One more up there.
I just have a quick one. Everybody, when you listen to the finance budget last year, I would have wanted to hear that they're going to pay teachers double.
I know.
What would you want to hear? As a person in the water research, what would be the ultimate, because you say it's an underutilized resource.
Yeah.
So in South Africa, what money could have been in a perfect world released in order to utilize this better? So what is the first step, just auditing what we have?
I think, and also training enough people. I think there should be a drive into educating and really getting, there are very few places to go and study this, and it's not taught from the beginning. So I think that education on our water, and WWF has been doing a great thing with that water doesn't just come from a tap, and that, so it's becoming now on the forefront. So education, but also supporting Department of Water Affairs and Sanitation, giving them enough money to actually, they used to have a lot more of a survey on and doing groundwater quality. So this has actually helped them, because now we can come and also help them do these surveys and get these baselines. So I really think investing into the protection and management. Again, you don't want to do a same project where you just look at what we have. We need to also start putting a lot more research into innovative options, and the Water Research Commission are doing a fantastic job. You actually, I think it's a cubic meter of our water, drinking water, they get a bit of money, and they manage their money so well, and they put out sessions where you can apply for research, and I could never have done my research without the funding from them. And it's because it's really great that that's happening, but it needs to be supported. And,
so you said they get money, so their ability to fund you, their money comes from?
Your water, so a bit of the water, it's a water tax if you can think about it like that. So they're doing...
Are they considered independent?
Yes, yeah. You should go to their website and just see. They normally actually poach all their experts and then make them research managers, and it's great. So, yeah.
Right. Do we have one more question?
Yeah.
You happy?
Yeah, that's fine.
Thank you. Hello. So I want to know, like, if I want to do something similar, or if I want to do something like you do, what would I have to study? Like, what would have to be my majors at the school? Instead of geology, like if I take geography, would it also lead me to the same path?
Yeah. Yes, geography is very important. Chemistry, if you can do science, I think it is really important for you to understand what's going on, just to even have you can be a physicists who focus on that, but I think maths and science and geography are very important in going, and then you do normally a BSc,
Yes.
And so in my case I focus on geology and chemistry. I really think you need to have geology. Some people don't have a geology base, but I think it's very hard to understand the dynamics if you don't understand the rocks, and that's the essence of it. But there are other people who focus on chemistry and stuff and use it in their hydrogeology. So, and then it depends. At UWC they offer a whole course right from the beginning. At Free State you do an undergrad and then you go and do another honours in groundwater, and then so. But I definitely, chemistry or science, maths and geography are very essential. Yeah.
I was very impressed that you mentioned that you wanted simplicity in the Atlantis project. And I think maintenance is terribly, terribly important.
Yeah.
You know, we hear all the time that the pipes are all maintained or something.
Oh, that's...
And training to be a hydrologist. My son is a hydrologist. I know it's a long training class. But would it not be possible to have barefoot hydrologists who work in the municipality, who know when some things need maintaining, or so I think in the present day educational circumstances, not everybody can be a fully qualified hydrologist or a pharmacist or whatever. And what can happen is barefoot.
We actually do, so you can actually do a technicon, but also you can go and join like Department of Water and Sanitation, and they do a trainee and then you become a technician. So they have that. Even the guys I'm working with, Atlantis, because they are working with the aquifer, they are becoming trained in groundwater and stuff. So you don't have to be also, you don't need to do this route, but you can still be involved. And some of them have gone and done water chemistry because they've got involved and they've learned on the job. So that's also something that should be funded. Is that?
I think that should be funded.
Yeah.
Thank you. That was a very useful question.
Thanks.
Any further questions? I think we're wrapping up now.
Yeah, I think so.
All right. So I think if I were a youngster in the audience today, I would go away thinking, thank you, Kate Robey, I'm going to be a hydrogeologist. So without further ado, I would like to thank you very much for giving us a fantastic lecture on this topic and really teaching us all something new. And I hope that everybody in this room can walk away knowing a little bit more about what they can do to look after their water resources and to contribute towards managing our water resources better. So thank you very much, Kate.
Thank you.